Welcome to Chemistry 111. Congratulations, I have everyone's tests. They've been come by at some point. You can get your tests. I'll return them. A few things to note as you look through it. One, did you read the full instructions? Did you put a smiley face? Smiley face was worth, 5 points. Bonus points. Were you late? One thing that occurred to many people. Did you use condensed electron configuration or full electron configuration? The full electron configuration should be self-explanatory. It's the entire thing. Condensed electron configuration takes the noble gas and shortens it and does just the valence electrons. If you did full instead of condensed and condensed instead of full, you lost several times. So that's a common thing that happened. Maybe not answering the question fully or not answering at all. Like, why does neon actually do this? Or what actually is the definition, not just the trend, or you're answering the wrong question. The common thing that happened. And what happened with at least a few people is there were two versions of the test. You should have checked which version you had. So if you tried to do test version 2 and you had test version 1, you're going to have bad time. However, if you feel your grade was unjustly given, that you could have done much better, I'm offering, say, a chance to take a short exam, figure this out, just a quick test to see, yes, I can do it. I just did it for the wrong numbers, because I'm trying to make sure you understand this. If you actually understand it and you didn't just copy it, you actually worked with someone and you worked it out and didn't just write down the answers, well, then an assignment would get you back. Some sort of assessment would show that you understand it and give you back some of your points. However, if you just copied, and then an assessment like this would not give you back any points. So I'll figure that out and try to get back with you and give people an opportunity if they want to try to get the assessment for a fraction of the points back. So I'll put that out for anyone, even the people who did the right test and still did maybe less than what they wanted to. But I'll send out more information a little bit later. Now we'll go back to chapter 7 in a bit. We're not going to get too far. We're not going to push too hard. I'm not going to go the entire time. I got a doctor's appointment I need to make it to. So, quick reminder is that some homework due today. Though should know how to do it pretty well. Chapter 5, periodicity and ionic bonding. Chapter 6, learning curve. Chapter 6.3 and 6.5, reading. Next week, remember, we're going to be on spring break. I'll be working on chapter 6, assessment. We'll definitely have finished chapter 7 before spring break. Not sure how far we're going to get into chapter 8 all before spring break. We might just leave that for afterwards. But okay, I just wanted to quickly show that before we look at chapter 7 again. Okay. I'm going to jump back a slide or two just as a quick reminder. What we are going to want to be able to do is look at molecular dipoles. That's one of the things we're going to be able to do. Quick reminder, there's two things to do to get a molecular dipole. One, look at electronegativity difference, which is the difference between, is essentially how well an atom can attract electrons throughout a bond. You're looking at the difference between two numbers. There's a nice little table. Typically, if we say the difference is larger than 0.4, it's polar bond. However, key thing to remember is nitrogen, oxygen, and fluorine and chlorine are pretty polar molecules. Pretty strongly, as long as they're not bound to themselves, it's probably responsible for a polar bond. The second thing to look at is the degree of symmetry of a molecule. Whether an atom cancels itself out, whether an atom is highly symmetrical, meaning multiple planes of symmetry, multiple degrees of rotation. Symmetrical, they tend to cancel each other out. And even though you may have a polar bond, you have a non-polar molecule. That's one thing you'll have to down. That this guy is highly polar, highly symmetrical. That you can draw a line right in the middle and reflect this side on this side. You could spin this guy like a ballerina with his toes down here, hands up there, and it spins and it's all the way symmetrical. This guy, which is water, sure, you could spin it around this little arrow and it could be symmetrical, but if I spun it in any other way, if I tried to spin it like a doing, it's not symmetrical. So that's not as symmetrical as, say, this molecule. This molecule, highly symmetrical. You can draw three mirror planes, each one through a bond. You could spin it like a top over the gray molecule and just spin it. All that's highly symmetrical. This guy is symmetrical so many ways. Symmetry all the way through the bonds, cleaving the atom in half, all of it. So many planes of symmetry. This one up here is symmetrical only kind of through this arrow. I can rotate it here, spin it like just on one axis, but I can't spin it on the other. No, this is on the XY plane, but if I try to spin it on the Z plane, not symmetrical. So that's one of the things that'll come up in the lab in a few weeks after spring break when we're looking at these bonds. Okay, I want to get into talk all about valence bond theory and sigma and pi bonding today. When we get through that, we'll see how we're going. So the idea between valence bond theory is the Vesper model is like the law. This is what happens. It's an observation without an explanation. It doesn't really say why this happens. It just says this happens. If I put 3 atoms off this or 3 electron domains off this, it adopts this shape. What we're trying to think is to reason out what's actually happening. Because remember, when we had our orbitals that we had available were s orbitals, p orbitals, d orbitals, and f orbitals. Those are the base orbital shapes. We had our s, which were like spheres, our p, which were like figure eights, our dumbbells, our bow ties. We had our D, which were like our flowers, and or like 4-leaf clovers, and F's like complicated flowers. So how do bonds actually form? When these bonds form, the orbitals must overlap. These orbitals, which is the potential electron density. This is the electron density of where the electron is actually located around this molecule, must overlap so that the likelihood of the electron of one atom is within the sphere of influence of another atom. And in fact, if we look at this chart, we can see there's a optimum bond distance. We start from very far away, very far away. This is zero energy point. These atoms are not interacting with each other. So there's no energy associated with this. As we bring them closer and closer together, we get a lowering of energy. This is a stabilization effect. As we get closer and closer together, you're actually storing some energy. You're storing the energy up till we get to the potential energy minimum. This is where we store the most energy. This is the optimum bond length where all this energy is stored. Over here, no energy is stored. We're at zero energy. We got the maximum attraction with the minimum repulsion. Most energy is stored. And then here, as we get closer and closer together, the energy is suddenly lost again. And in fact, the energy goes up as we get to the whole fact where attraction is countered by repulsion. We've gone the atoms too close together. And now the nuclei, the big positive centers, are starting to repel each other. It's no longer the electrons are interacting, it's also the nuclei are interacting, and so they start to repel each other again. And so we're losing the energy we saved, and then some. So you're smashing atoms together. It takes a lot of energy to push these atoms together, just the same way as if you have two magnets of the same pole and you try to push them together, they're going to want to fight against you. You can do it, but it's going to take work. So there's going to be some degree of interaction as we bring them over. And so the orbitals need to overlap at an ideal distance. Too close, and we get repulsion. Too far, and we don't get much interaction at all. In simple molecules, we can imagine just a simple S-S overlap like in hydrogen, or S and P overlap like in the case of HCl. We don't have to do anything really fancy because we put one electron in the P, overlaps with one electron in the S. And we can imagine the overlap right here. However, it gets a little bit more difficult when we talk about things like water. I'm moving my face down here just temporarily. Case of water, if we did that same judgment, if we did that exact same thing, you would expect a 90-degree angle because the p orbitals occur on each of the axes. You have a p orbital on the x-axis, a p orbital on the y-axis, and a p orbital on the z-axis. If you think about it in terms of that, each axis is 90 degrees apart from each other. 90 degrees apart. So if I simply used our p orbitals that are readily available in the water, you would expect a 90-degree bond angle from, say, a px and a py as they interact with two separate s orbitals on the hydrogens. However, if you look at water, you actually get that the bond angle is 105. It may not seem like much, but that is 15 degrees difference. And that is not readily explained by our simple bonding rules. Now, this actually occurs because we form what's called hybrid orbitals. What a hybrid orbital is, let's break out what hybrid is. If you have a hybrid plant, you've mixed the genomes of two different plants together to give it some new property, some new like phenotype. You've swapped together something that makes this fish glow in the dark or makes this plant glow in the dark. Well, a hybrid orbital, we're going to swap together. We're going to mix together two different types of orbitals and, in effect, give them the properties of both. So when we do this, there's going to be an energy cost. There's going to be energy cost. It's going to take some energy to combine multiple orbitals together. But when we do this, this is going to minimize electron repulsion. And all the hybrid orbitals that we generate will be degenerate. What does degeneracy mean? In terms of chemistry, it means of equal energy, of identical properties. When we talked about all the p orbitals, we said all 3 p orbitals were degenerate. So I could put electron in any of the p orbitals. It didn't matter which one I put in first, as long as all of them get put in before I pair up the second. I could have gone orbital 2, orbital 3, orbital 1. I could have gone orbital 1, orbital 3, orbital 2, as long as I put one in each before I paired them up. Well, when we make these hybrid orbitals, there's going to be a little bit of energy cost, but I'm going to make multiple degenerate orbitals that are going to be optimized for bond making. And when I make all these bonds, the final structure will be lower in energy than we would have had otherwise. So, now looking at this, what we have here in the top quadrant right here is a standard hybrid orbital for, let's see, 1, 2, 3, 4. 4 valence electrons. That is a carbon. 4 valence electrons. Remember, when you're doing formal charge, you compare your valence electrons to the electrons around the molecule. We have 2 in the s, which are low energy, and 2 into 2 separate p orbitals. If you imagined trying to make bonds, we try to make bonds with unpaired electrons. So looking at this 2s orbital seems pretty happy. It's going to be pretty close to the molecule, hard to make bonds with. And we really only have, we really only have 2 electrons to work with, 2p. However, if we combine the s and the p together, we're going to make 4 new orbitals. If we combine the s and all of our p together, we're going to make 4 new orbitals, all of the same energy. If you look here, the s orbital shifted up a bit in energy, but the p orbitals shifted down a little bit in energy to make 4 new orbitals. We combined 1 plus 3 to make 4 new orbitals, because carbon has 4 electron domains. So we're going to make 4 hybrid orbitals to match those 4 electron domains. When we make hybrid orbitals, we're always going to take some amount of one s and some amount of p until we match with the electron domains. Now, carbon, as I said, typically has 4 electron domains. In the case of 4 electron domains, we combine 1s and 3p to make 4 new orbitals. So let's look at these orbitals. S is like it's a non-directional sphere combined with these lobes. What the result is when we combine these lobes is we get something that looks like a strong man who only lifts with his right arm. He's only got one big bulky bicep and the other one is teeny tiny. It's because this kind of shrunk and this kind of grew as the S interacted. Now, we're only going to interact with this small bit of the big bit of the S, the orbital, not the small bit. And so when we combine these together, these guys are no longer stuck on the axes. These are going to arrange themselves so that we can make all the bonds we need. These guys are going to arrange themselves that 109.5 distance away. So when we combine 1s and 3p, we make 4 new orbitals, which we call the sp3 hybridized orbitals. sp3 because we used 1s and 3p. If it's 1, we're going to leave it blank for the understood 1. But if it's ever more than 1, we're going to sp3. So 1s and 3p makes 4 sp3 hybrid orbitals. All tetrahedral geometries, all structures that adopted tetrahedral electron geometry will be dealing with sp3 hybridized orbitals. So CH4, the structure CH4 is tetrahedral. It will have sp3 hybridized orbitals interacting with 4 hydrogens. NH3, ammonia, will have is tetrahedral structure. We would call it trigonal pyramidal in shape. It would interact with 3 hydrogens and have a lone pair on the empty orbital or the unbonded orbital. Water, which is H2O, is tetrahedral in shape. It would have 2 bonds from the hybridized orbitals and 2 lone pairs in the unbonded hybridized orbitals. So any electron domain geometry we can get is going to be directly related to a hybridized orbital. Now, this is where we get into a certain type of bonding. Now, you may think, why do we need to specify the type of bonding? It's just, well, a single bond. Well, we're going to talk about what type of overlaps we have. The simplest one is just a single bond, which we call a sigma bond. A sigma bond is just a simple one-to-one overlap. We have a singular overlap between 2 orbitals of any type. Every time there is a single bond, we have a sigma bond. And all atoms will start with a sigma, and we can go from there. So hydrogen, the H2, would be experiencing 1 sigma bond. An H and a Cl would draw that just a sigma bond. A Cl only needs 1 pair of electrons to give it an octet. So it's going to be just a sigma bond between our 2p orbitals. Hybridized orbitals, this CH4 has 4 sigma bonds because it has 4 single bonds. This structure is a complicated one. This is ethane, which is C2H6, but essentially it's a CH3 single bonded to another CH3. And that one has 7 sigma bonds. 1, 2, 3, 4 in the middle, 5, 6, 7. All this singular overlap is a sigma bond. Now, why are we going to specify this? Because in a minute, when we talk about other types of hybridized orbitals, we're going to talk about other types of bonds. But the basic thing to think about is every starting bond will usually start with a sigma. Every starting bond, when you draw that first bond, will be a sigma. Anything from there we'll talk about later. So in a trigonal planar molecule, remember trigonal planar has 3 electron domains. 3 electron domains. So it's going to require 3 hybrid orbitals. To make those hybrid orbitals, we would take one s. Always we start with the one s and 2 of the p orbitals to make 3 new orbitals, which we're going to call the sp2 hybrid orbitals. sp2 because we're making it with one s and 2p. And we call that molecule sp2 hybridized. When we take the s and the p to make new hybrid orbitals, they look pretty much the same as the sp3, except they're going to adopt the trigonal planar geometry when you combine them together. Another thing to note is that when you hybridize 2 out of the 3p, that third p stays behind. That unused p stays behind. That was there all along. It's not going to be used. It's not going to be hybridized. So it's going to remain like a p orbital does with the double lobe. The double lobe. And that's going to be important in just a minute. And that what the other type of bonding that we'll experience here in this class is called a pi bond. Like 3.14, that type of pi. A pi bond. Well, the pi bond, if a sigma bond is a singular overlap of 2 orbitals, a pi bond is going to be a double overlap of 2 different orbitals. Now, the only way we could get a double overlap is with these, mostly with these p orbitals, these unused p orbitals. Because if you bring 2 orbitals head to head, they're just going to touch, like in here. But with these p orbitals, these double lobed, they can overlap at top and they can overlap at bottom. And so what we get when we look at the pi bond, we get a double overlap, like a double envelopment that surrounds our sigma bond. So that purple bond in this picture, hopefully you're not colorblind and this is appearing all right on your screen. Purple bond is your sigma bond. These pink bonds are your pi bond. And so every type of pi bond is going to involve a double overlap like this. And so you need that p orbital there to do that. To do any type of pi bonding. And why do we need to specify pi bonding versus sigma bonding? It has to do with strength of bonds and ability to move electrons and all stuff that will become very important, especially if you ever go into organic. If you go into organic at all, this is something that you really, really need to understand. So we'll work through this. But basically speaking, to start off, every single bond will start with a sigma bond. Every additional bond, and every bond in addition to the sigma, will be a pi. Every bond in addition to the sigma will be a pi. So in the case here, we're looking at here, the ethane molecule, we have 1, 2, 3, 4, 5, 6, 7 sigma. In here, would count all the bonds once, 1, 2, 3, 4, 5. 5 sigma bonds, and the additional, the second bond here, would be a pi bond. To make a double bond, you need a pi. To make a double bond, you need a pi. So we have 4 CH sigma bonds, 1 CC sigma bond, and 1 CC pi bond. That is the molecule we're looking at in that picture. In linear molecules, 2 electron domains are needed, and so they require only 2 hybrid orbitals. 2 hybrid orbitals. When we combine them together, we use 1s and 1p. 1s and 1p. When we do that, we form what's called the sp hybridized orbital. And we only form 2. We get 2 hybrid orbitals. Because of that, we leave 2 p orbitals behind. We're going to adopt what called the linear geometry between those 2 sp orbitals. And now we have 2 pi orbitals that can undergo 2 p orbitals that can undergo pi bonds, depending on where the interaction is. Right here, this is ethyne, C triple bond C. CH triple bond CH. In this case, we see an envelopment top and bottom, and you can't quite see it, but we'd also see an envelopment front and back. But the idea here is we have a double envelopment from both of the p orbitals. A double envelopment from both of the p orbitals. You'd also see this situation in nitrogen gas. It's a diatomic. It would see a double envelopment because nitrogen gas is N triple bond N. You'd also see this situation in CO2. However, there's no triple bonds in CO2. There's just going to be a double bond between one CO and a double bond between the other CO. But the idea here is that both p orbitals on the central carbon would be utilized in making pi bonds. These are our basic shapes here in our linear geometry. We have sp hybridized orbitals and would make you'd use the unused p to make these pi bonds. But before we go here, there is 2 more shapes we won't really worry about. It will happen on occasion, and it will come up on the lab, not so much on the homework, not so much on any test. But so far, we've gone through 2 electron domains, 3 electron domains, and 4 electron domains. But notably, we've left off 5 and 6 electron domains. If you noticed, when we used the 4 electron domains, we used 1 of the S and all 3 of the P. So how are we going to get 5 electron domains? We've used up all of our S and P orbitals. Well, that's where we're going to start to use up d orbitals. So when we make 5 electron domains, we're going to have what's called an sp3d orbital, hybrid orbitals. It's going to make 5 orbitals for 5 electron domains. If we need to make 6, we're going to have an sp3d2. sp3d2. And before you're like, oh, God, these aren't in the notes. If you look at the lab has a direct reference. If you can figure out the correct number of electron domains, you can figure out the hybrid orbitals because there's a direct correlation. We will only go up to 6 electron domains, so we will only utilize 2 of the d orbitals. At most, 2 of the d orbitals. But it's simply the same kind of thing. We'll make equal amounts of these like weird hybrid orbitals, and they will adjust themselves so they make the correct shape. Now, one of the reasons why we differentiate between the pi orbitals and the sigma orbitals has to do with the resonance structures and pi bonds. So the idea here in resonance structures is that all the sigma bonds are localized. All the sigma bonds are stuck in place. They will not move. All the pi bonds are going to be delocalized in that, if you look here, this is a structure for C6H6 or benzene. When you draw the structure, benzene has 3 double bonds, 3 pi bonds in there. Depending on how you fold these p orbitals depends on where you draw the double bonds. This hexagon shape, you could draw the double bonds here, or you could draw the double bonds there for 2 different, what they call in organic Kekulé structures, where they localize the pi bonds. However, these guys are like palm trees that blow in the breeze. Strong winds can blow them from one position to the other. They're allowed to switch around. It's a very low energy transition. Because they are allowed to switch around, they are not localized. They're delocalized. They're movable. They could fluidly move throughout this. And so what we get is a stabilization effect where we delocalize the electrons through the entire ring. So we look at almost the entire ring being double bonded instead of just 3 single double bonds. The same thing with NO3. NO3 1 minus has 2 lone pairs and 1 double bond. 2 lone pairs on each oxygen and 1 double bond. Well, I could easily move this electron from the lone pair down and attack this nitrogen and kick this guy out as a lone pair, this bond out as a lone pair, and basically swap this double bond between each of the 3 oxygens. In each of the 3 oxygens. So what we end up having is a delocalization effect throughout the entire molecule. So each oxygen is essentially resonating with that double bond. Anytime you have double bonds and lone pairs, you could usually see in close proximity, you could see this resonance effect. This resonating stabilizes all the bonds. So even though if you draw CO3, 2 minus, it doesn't look. I'm going to jump back a couple slides just to go back to what we talked about at the very beginning of class. This right here is CO3 2 minus. Even though CO3 2 minus, you draw CO3 2 minus, you should draw 1 double bond to an oxygen and 2 single bonds with lone pairs. Even though 2 of the oxygens look different from the third, the resonance structures average the whole thing out, so it is actually perfectly symmetrical. So even though you draw, well, here's a double bond and here's 2 single bonds, it doesn't look like it should shift. If you draw the 3 resonance structures, they are the same. They are the same. And so we need to remember that as we talk about these resonance structures, as we deal with these pi bonds. These pi bonds are delocalized, which is why we're going to have to remember that, which is why the resonance structures are so important, why some of these molecules are actually symmetrical even though they don't look symmetrical. Another thing to note is anytime there is a sigma bond, there is free rotation allowed. We can adopt various different shapes, various different what we call conformers. The atom with the same structure and connectivity, but a different overall 3D image. That's because when we have just a head-to-head overlap, it can still rotate around that head like a ballerina doing a pirouette and still keep the same connectivity. And so this molecule on the left is identical to this molecule. Maybe not perfectly the same energy, but it is the same atom. It is the same molecule. It's a different conformer. One might be a slightly higher energy than the other, but they are the same. You would give it the same molecular formula. It's the same. However, when you look at the pi bond, because it is a double envelopment, an overlap of top and bottom, we cannot see the same degree of rotation. We cannot rotate the same way, because if you start to rotate, you will break the pi bond. You rotate it 90 degrees, suddenly you cannot get that same overlap. Pi bonds will lock in the rotational structure, while sigma bonds usually allow for free rotation throughout the structure. It's one thing to keep in mind when you're looking at larger structures. Okay, we will probably go ahead and stop here because molecular orbital theory is a beast. We will try to get into that. Molecular orbital theory essentially will go into what actually is occurring in the bonding. Why are some structures stable and some structures not stable? And it's trying to get deeper into explaining why this works or this doesn't work. So, and it uses some like wave theory where you're talking about like waves adding and subtracting, and that it's not going to be something we're going to discuss too heavily for the test, but it's something that since we have the time, I will try to go relatively in depth on it, at least as best we can, because this does come up in organic chemistry for those of you who will have to have that. But with that in mind, I'll go ahead and stop there because I do not want to get into that today. We spend a good deal of time. Quick reminder, don't forget the homework if you haven't already done it. Come get your test at some point, and I'll talk more with you guys a little bit later.